Fine.
Yes.
I'm sorry for
Absolutely fine.
this delay. Okay.
Ania, will you introduce, please?
I don't hear Hania. What is happening?
You will hear it her soon. Hania, introduce.
I'm hearing you, Imran, but
Right. Hello, Assalamu alaikum, everyone. Welcome
Hello.
to John Conway's series of seminars at Math Department Lungs. It is great pleasure to introduce and welcome Professor Rached Mneimne from University of Paris. He is going to talk about classical Lie groups and homotopy theory, and he has expertise in representation theory of Lie algebras, groups and their homogeneous spaces, semi-simple Lie groups in their homogeneous spaces. And of course, he's a very prolific author of several very, very popular books in France, ranging from higher linear algebra to finite groups and analytic geometry. So it is an honor to have us amongst us. And over to you, Professor Rached.
Thank you, Hania. Thank you, Imran. Hello, everybody. I'm sorry for this delay, but I have had a small technical problem. It seems that it has been we are able to communicate. Okay. So let me begin with an introduction. We are going to look at some topological features of chosen collection of small number of classical Lie groups. I will say in a moment what is it, a Lie group, and what is a classical Lie group. Working with a vector space over a field K, which we call it V, a chief priority is to examine the linear group GL of V, which is the group that controls all the geometric setting. Okay, I'm reading what is written in front of me. Once a basis is fixed in V, we may shift to matrices and focus on the group GLN of K, where N is the dimension of the vector V as a K vector space. Here, the basic field is R or C. Anyone who has worked with both R and C will tell you that the complex setting is easier than the real one. Indeed, it is notorious fact that the field C is more generous than R. For instance, look at the equation x to the power 3 minus 1, not to mention the famous equation x to the power 2 plus 1. This first equation, x3 minus 1, has just one solution in R, while it has 3 in C. More freedom in C also. Take out a finite number of points in R, and the same in C, and let us say that this number is equal to K. You find yourself locked in K plus 1 components in the first case when you are in R, and you can still move freely while you are in the second. This means that C is not only give you enough roots for an equation, but still, if you take out some points of C, you still have a connected path, connected set. So what we have in mind? We have in mind the homotopy properties of a certain number of classical Lie groups. We must nevertheless begin by looking at their basic topological properties, connectedness, compactness, etc. And of course, begin with the most visible one for us, namely the group GLN of K itself. The topology we are dealing with is, of course, the dual topology on the set of square matrices n times n over the field K, which has a different way to be to design by notation. Okay. No, now, why GLN K equal R or C is an open dense subset inside the set of matrices. Of course, we have equipped the set of matrices, which is a finite dimensional vector space, with the natural topology. Okay, and GLN K appears as the inverse image of an open set, which is exactly K, which we have taken out the point 0. And this is an open set inside of K, and we take its inverse image by the continuous map given by the determinant. So this settles the openness. Okay, it's an inverse image of an open set by a continuous map, so it is open. As for density, if we take a given matrix M, we should be able to find a sequence of invertible matrices which are convergent to M. Take, for instance, the sequence M minus the identity over K, and if we make K go to infinity, it of course converges where M towards M, and in the same time, these matrices, as soon as K is enough big, will be invertible. Why? Because 1 over K is outside the spectrum of M once K is enough big. Okay. Another way to prove it is to prove that the identity is an interior point of GLN K. Once we have proved it, we can, by translation, prove that any other point is interior to GLN K. Translation by multiplication here, okay? And how we could show this, we take the identity and we are going to prove that SM is small enough, IN minus M is invertible. And we can show, we can have its inverse as a sum of a series which is very classical, which is the geometric. Why this series is convergent? Because it is convergent in norm. We have taken the norm verifying this inequality, and if the norm is chosen like this, we can prove that series is convergent in norm, and since we are in a vector space, it is convergent. Okay, a series which is convergent in norm will be convergent. Another way to prove this is the following. Okay, so let me erase this argument. Sorry. Okay, so we are here. We have proven that the set is open in M and K. We have proved that it is dense. There is another way to prove that it is dense. It's easy. GLNK is the complement of a Zariski point, the closed set. Let us take the set of matrices of determinant 0. This is a Zariski closed set. It is the 0 of a set of polynomial. Its interior is void, because if not, the polynomial determinant will be 0 over an open subset in K to the power n. So it will be 0 all over. But this is not true because the determinant is not 0. Why the determinant would be 0 if it was just equal to 0 in a neighborhood of a point? Because use, let us say, the Taylor formula in several variables. In the case of a polynomial, it stops at the moment it is. And if you have all the derivatives which are 0, the polynomial will be 0. At the point, the polynomial will be 0. So this is a very classical argument which we should keep in mind when we are working with Zariski closed sets. Okay, let us pass to the path connectedness of GLNC. Now we see that GLNC is open, it is dense in MNC. I'm trying to prove you that it is connected inside as a space, as a topological space, path connected. This is not the case of GLNR. You see why? Because GLNR, when you apply the determinant, it goes surjectively on the set of non-zero real numbers. So this is not connected. So GLNR is not connected. Okay. And as I said in the beginning, the case of C is easier. GLNC is connected. Well, how? I will give you 3 arguments. First one, very easy, very quick. It is the following. Take the exponential map, which goes from MNC to JLNC. Why it arrives in JLNC? Because exponential of A is invertible and its inverse is minus exponential minus A. And this map, which is continuous, is surjective. It is surjective. It's an easy exercise in linear algebra. And since MNC is path connected, it will be the same for GLNC. So this is a first argument. Exponential, I recall you, it's the sum of the series m to the power k over k factor. This is again a series which is convergent in norm. So we are in a complete vector space, so it is convergent. And the exponential has the classical properties. Let us say this one, for instance, determinant of exponential A is equal to exponential to the trace of A. Another way to see that the exponential is invertible. So this is an argument. Another one, I will erase. Another argument is the following. Here again, we have the set of matrices of determinant 0. This is a Zariski hypersurface, closed hypersurface. And in that case, the complement is always connected. Let us show it easy. Take two matrices A and B, which are invertible, and consider the set ZA plus I minus ZB for Z in C. This set could be made of invertible matrices as soon as ZA plus 1 minus ZB is of the determinant non-zero. And it is equal, this determinant of ZA plus minus M and Z, it's a polynomial in Z. So it has a finite number of roots. And since it has a finite number of roots, the complement would be connected, pathwise connected inside of C. And so we can put A and B in a pathwise connected subset in GLNC. By taking this set, once Z is chosen like this, non-zero. So we have each two elements can be put inside a path connected subset, and then they are connected. Imran, I'm not hearing you. You are speaking with me? No. Okay.
I have a question. I have
yes.
a question. So what is the continuous group action? So which
I don't hear you quite well, maybe a little bit higher.
So what is the continuous group action you will use? Which continuous group action you will use?
For the moment, I have no group action. For the moment, I'm looking to two invertible matrices, and I find a path which connect them. How?
Okay.
So
we will see. So we will see continuous group action in further slides.
Later. For the moment, there is no group action for the moment. Okay.
Okay.
For the moment, I haven't spoken about group action for the moment. It will come in a moment. Okay. So I am giving some arguments to prove that GLNC is pathwise connected. So this is the exponential map is one, passing by the fact that it is the complement of a Zariski hypersurface. It's also another one. This is the argument, very easy, very nice. It's the easier way. And there is a third way, which is quite good also, which is the following. If you know that each matrix in MNC is similar to a triangle matrix. Okay, so GLNC is the union of all these sets. Okay, if I take the invertible triangular matrices, that means these matrices here, it's non-zero. and here any number. This set is pathwise connected. Why? Because it is the same as C star to the power n times a vector space, which is the strictly upper triangular matrices. And if you take the union of connected subsets which intersect non-trivially, all these sets contain the identity, and you have a lot of them which are connected, so the union is connected. This is a very easy argument if you use the fact that any matrix can be reduced to the triangular form. Okay.
So this forms the conjugacy classes actually. I guess.
Repeat.
So these are the conjugacy classes. These are the conjugacy classes you are talking about.
Yes,
so
I take the set T and C, okay, T star and C, and I take all its conjugates.
Okay.
So the union is
the conjugacy classes.
Okay. The conjugacy classes of T star and C. Okay, I take I take the conjugation of this set. I get a new set which is still connected, and I take the union of all these sets and I get GL and C. Since these sets intersect non-trivially at identity, let us say, there is a point in their intersection, so the union will be connected. Okay, pathwise connected. So this is a third argument, which is very nice also. We will give a fourth argument using group actions, okay, in a moment. So let us now come to group actions. I have a set X, and I have a topological groups, a topological group which is acting on it. X is topological, Hausdorff. The same G is a topological group, and I suppose that the action is continuous. I will not define this, but you imagine what does this mean. And inside of X, I take a point and I take its orbit. Its orbit, I will denote it G point X0. And we have, of course, everybody knows, as soon as he or she has worked with the group action, that we have an equivariant map between the quotient of G by the stabilizer of X0 and the orbit. And this map is the following. It sends the class of J modulo G of X0 to G point X. And this map is equivariant. Let me explain again what is it. X is equipped with a G action, so the same as for the orbit, which is stable under the action by definition of the orbit. And here it is what we call a homogeneous space. We have an action always of G over the quotient of G by any sub of its subgroups. And this set has a fixed point. Okay. Are you seeing me?
We can see you, but not.
Kindly share your screen once again. I'm sorry.
I must share my screen.
Yeah.
Okay. Fine?
Yes. Thank you.
So
sorry for me.
What I'm saying that when you have an action of a group G on a set X, you have for each point inside of X, any element X0 inside of X, you get what we call an equivariant bijective map between the quotient of G by the stabilizer with the orbit. And of course, if the G is acting continuously, this map will be continuous once we equip the quotient set G over the stabilizer of X0 by the quotient topology. And the orbit by
the action must be. So I have a question. So the action must be transitive.
It is transitive because I'm working with the orbit.
Yeah. So in this case, we must have a transitive action.
What?
So in this case, we are dealing with the transitive group action.
Yes, even if X is not, if the action on X is not transitive, once I look at the orbit, it becomes transitive, okay?
Yes, so it's transitive on the orbits, but it must also be transitive on the topological space X also, isn't it?
No, you don't need to have it transitive on X. You are. I'm just looking at the action over the orbit, and over the orbit it is transitive.
Yes, on the orbit
While the
it is
action on
transitive.
the action on the homogeneous space is transitive. Okay.
Yes.
So we have on the left a transitive action, on the right a transitive action on the orbit, and these actions are quite good. There is an equivariant map, and what I'm asking for is this map, which is bijective. Is it an homomorphism? In general, it is not. Okay. Let us see, for instance, when it happens, if J is compact, the quotient is compact. Here you have a bijective continuous function going from a compact set to a Hausdorff set, which is bijective and continuous. So it will be a homeomorphism. So it is easy in the case of a J, of a compact set, of a compact group, that the equivariant maps are all continuous. But in general, this is not the case. It happens that it is the case in a very common situation for us if the group has these following conditions satisfied. If J is locally compact, countable at infinity, that means it is the union of an infinitely of a dénombrable of countable number of compacts. And if the orbits is also locally compact, you see we have three conditions. Of course, if J is countable at infinity, the orbits are also countable at infinity. So we have these conditions. In that case, the equivariant map phi and this x0 is a homeomorphism. This is very important. And
what do you?
I'm not hearing you quite well, please.
Can you elaborate what you mean by countable at infinity?
Countable at infinity, that it is the union of a countable number of compacts.
Oh.
Okay. Any open set inside Rn is countable at infinity. So GLNK is countable at infinity. It is the union of a countable number of compacts. So if you have this condition on G and you have and the fact that G is locally compact, then this bijection, which is continuous, is bicontinuous. And we'll keep this in mind because this is a very excellent result, which is not always the case. You have a lot of orbits which can be far from being locally compact, and things may turn very bad. So here in this situation, we can be happy because GLNC will work with it. For instance, how we can prove that GLNC and GLNR are both connected. Let us see. I take GLNK, okay, and I let it act transitively on this open set. Okay, but just by the tautological action, a vector non-zero, I take it by the by P on P de V. This is the action, and the action is transitive. Why? Because any non-zero vector can be put inside the basis, and when you take a basis to another, you can prove that the action is transitive. And what is, let us say, what is the stabilizer of this? It is the set of matrices which looks like this. So this is GLN minus 1k, and this is a vector in k to the power n minus 1. So we have the situation like this: GLNK over kn minus 1 GLN minus 1k, bijectively homeomorphic to this set. So you see, if we make an induction, knowing that GL1 of C, which is C star, is connected, we can get that the quotient here is connected. And if we admit that GLN minus 1 is connected by induction, we can say that GLNK has the property that its quotient is connected because it is homeomorphic to this, which is connected as long as K, we are working with C. And the quotient, the subgroup by which we have quotient is connected. We have a classical result. If J over H and H are connected, then G is connected. Okay. I'm sorry. Voilà. Okay, let me try again. What's happening? Okay. Je savais faire ça. Tout le monde, je sais plus faire. Oui. Okay. Bernhard will come and help me if he is kind enough, and he is kind enough. So, okay, let's go and see what is happening in the case of GLN plus, because GLN plus happens to be a little more difficult. We do the same, okay? We make GLN plus, that means a set of matrices of determinant 0, a determinant strictly positive, and we make it act again on KRN minus 0. And in that case, working with the GL1 is connected from the situation 1, and we can again make an induction. Bernard, tu me dis comment faire pour effacer? Just si on passe tout, tu peux effacer tout. Okay. Okay, fine. So now that we have proven the fact that GLNC is connected, GLNR is connected also, plus, of course, we see that GLN of R has two pathwise connected components. Okay. Ça va pas aller. Je suis panique. Voilà, good, fine, fine. It's done. J'ai réussi. Now we have proven this. Let us go to the unitary group. What is the unitary group? It's a set of matrices such that the inverse of U is its transconjugate. That means this. So this set is a group, very interesting, and we shall prove again that it is connected. How? We make UN act on the unit sphere of Cn with respect to the Hermitian product. Okay, we have a product here which is the usual Hermitian product on Cn, and if we UN conserves the norm associated with this Hermitian product, and we have here again something like this: UN over UN minus 1 is homeomorphic. Here UN, I will tell you what is happening, is the unit sphere of Cn. That means it is the sphere of dimension 2n minus 1. UN is compact. This is very important. Why? Let me give you a proof very quickly. Okay, the UN is made of matrices such that their columns are orthogonal with respect to their Hermitian product, and each column is of norm 1. This means that the set UN is bounded, and it is clearly closed. A bounded closed set inside the set of matrices, okay, is of course compact. So UN is compact. We don't need the hard part of the theorem about the group action. So UN is compact. An induction starting with the fact that U1 is the circle, prove that UN is connected. We can do the same with SUN, which is the set of matrices which are in UN and of determinant 1. And since SU1 is just the 1, we can do by induction SUN is path connected. This is easy because the part which was here and the edge in the case of GLN disappears, since our matrix will have 0 here and it will be orthogonal. So all this part will be 0. So we have this writing. Let us see another case quickly again. Don't hesitate to stop me if there is the need to. If we work with SON, it is the set of matrices such this equal n and determinant of M equal 1. ON cannot be connected because the determinant send it surjectively on plus or minus 1, a matrix such that TMM equal to identity. If we take the determinant, we find that determinant of M square equal to 1. So we can have plus and minus 1 as determinant plus. If we take the determinant 1, we have something like this: SON quotient by SON minus 1 is the sphere of Rn. That means this. And an induction will give us that SON is connected. Okay, so we have a lot of things which are nice to do with. And now I will pass to something very important, which is the polar decomposition. Is there any question till now?
Yes, okay.
Okay, Imran? Okay, so we keep in mind UN, ON are compact groups. GLN is connected in case of C. GLN plus is connected inside in case of R. And SUN and UN are both compact and connected. SON is connected. SON is not connected. It has two pathwise connected pieces. Okay. So let us see this result, which is important by its own. Theorem, call it the polar decomposition. If we begin by an invertible matrix and there exists a unitary matrix U and a positive definite Hermitian matrix H such that P equal to UH. The matrices U and H are unique. Moreover, the map which appear here, okay, UN times H plus. This H plus is the convex set of Hermitian positive definite matrices. That means H star equal H. This is the Hermitian property, and positive definite, that means all the eigenvalues are strictly positive. Okay, eigenvalues strictly positive. So this set, which I denoted H plus, is convex and it's a half cone. If you multiply by lambda positive, real positive, you're still inside. And here we have a homeomorphism. What does this imply? It implies again that the topology of GLNC, which is connected as the one of an HN, this one is convex. So there is no problem that with its topology. UN and GLNC are essentially have the same topology as it comes to algebraic topology, because the part H++ N is, we will see, Euclidean. Let me show it. Okay. So again, okay, there is a real version for this polar decomposition. UN replaced by ON, and H++ is replaced by the set of symmetric definite positive definite matrices. So a very important fact that the exponential going from the set of Hermitian matrices to the set of positive definite Hermitian matrices is a homomorph. And this set H of n, the set of all Hermitian matrices, is a vector, is a real vector space of dimension n to the power 2. A very straightforward argument is the following: MNC can be written as the set Hn direct sum Hn. This is the set of Hermitian matrices, and this is on the right the set of anti-Hermitian matrices, and they are this is the usual decomposition of a matrix as symmetric and anti-symmetric. Here we take it Hermitian and anti-Hermitian, and they are with bijectively isomorphic as a vector, real vector spaces. Here the space is of dimension 2n squared. This one will be of dimension n2, and this one will be of dimension. And so this is essentially R to the power n2, which is isomorphic to this set. So again, GLNC up to an Euclidean vector space of dimension n squared is the same as UN. So if we want to study GLNC, we are supposed to study UN. We can have, I have thought that I would give you the proof, at least in the case, the real case, because here again we have GL plus it's homeomorphic to n times the symmetric matrices S++, which is homeomorphic to S by the exponential. If you take a symmetric matrix and you take its exponential, you get a symmetric positive finite matrix, and you have here an homeomorphism. So here again, this set is a vector space of dimension n times n plus 1 over 2, and you get that GLNR topologically is essentially as ON. Now, a very nice fact, which I will give you here in a quick way. If we have the polar decomposition, it is easy to prove that UN is compact maximal subgroup of GLNC, and the same for ON is a compact maximal subgroup of GLNR. And all compact maximal subgroups of GLNC are conjugate to UN, and the same for GLNR, or its conjugate maximal compact subgroups are conjugate to the orthogonal group. This means that the orthogonal group and the unitary groups can be naturally present as soon as we look for compact subgroups of GLNC and GLNR, and the topology of GLNC and GLNR is essentially up to a Euclidean space, the topology of one of its compact maximal subgroups. I'm sorry. So how we prove this? Let me give a very quick proof. Okay, if you take UN and you put it inside a compact set subgroup, compact subgroup inside of GLNC, we must prove that K equal to UN. Take a matrix P inside of K, write its polar decomposition. P is H. So H belongs to K, since P and U belongs to K. But if H belongs to K, all the powers of H belongs to K. So K in Z. So all the powers of H are in C, in K. But if you take any the trace of H to the power K will go to infinity. Why? Because one of the values, eigenvalues, will go to infinity. If it is greater than 1, the power of it will go to infinity, and if it is greater than smaller than 1, strictly, you will have it by taking K negative. So all the values, all the eigenvalues are equal to 1, and this means for symmetric matrix that it is equal to 1. So you see, P is equal to U and P is in K. So this is a nice proof that the unitary group is a maximal compact subgroup of GLNC. Let us pass to the ONC. Now I'm looking for a special group which is not ONR, which is not UN. It's the set of matrices which are orthogonal inside of C. That means transpose of P is equal to P minus P in GLNC. So this set is denoted by UNC. It's the orthogonal complex matrices. It's not the unitary group. And what happens here, that this group is homeomorphic to the product of the orthogonal group by this set denote the anti-symmetric matrices, which is a vector space of dimension n minus 1 over 2, n times n minus 1 over 2. So if we are looking at this homeomorphism, it can be deduced from the polar decomposition of a general invertible matrix. I have written here the proof, which is quite easy. We have the fact that ONC is, again, its topology is the same up to a vector space as the same of ON. In particular, it has two connected components. And if we take SON, SON will be, SONC will be connected like SON. Now, why I need this group? Because I will have an application at the end with this group. Now, let us pass to our of the core to our subject, which is the homotopy. I suppose that you know already what is the fundamental group at the point. Okay, if we take a pointed set X pointed at the point 0, we can send this pointed set to a group which is called the pi1, the fundamental group, and this gives us a covariant functor from the set of pointed sets to the category of groups. This is the first fundamental example in algebraic topology when we go from topology to algebraic structure. And this happens with P1. P1 is the set of all classes of paths of homotopic loops. You take a loop in X0 and you take its class modulo homotopy, and you take the classes of all homotopy, the set of all homotopy classes of loops, and you get a group. For instance, if you take out of C a point, a loop is essentially the way it turns in one direction or another. And so the P1 of C star is essentially the additive cyclic groups. I suppose that you already have seen this before. So let me say something more about this. The pi1, the P1, the fundamental group is multiplicative. That if you take the product X times Y of the two topological spaces, pointed at this point, it is the product of this. So points, so now I will need a notion which is very important for my computation, which are going to follow. If I have a set which will be called the total set, and B is the basis set, and a map phi from T to B, it will be called a good vibration if it satisfies these three properties. The first one, all the fibers of phi are homomorphic to a non-empty topological set F. In particular, phi will be, so this is the picture is the following. You have B here, you have T here, and each point has a fiber over it, which is the same. So all the fibers are homomorphic. And what else? Any pass inside of the base can be lifted. So if you have here a point x0, and I take the fiber which passes through x0, this is a phi of x0. So if I have a pass here, that means a map going from 0, 1 to B, I can lift it by a condition. That means I can suppose that I can lift it here. So the lifting of F tilde will goes from 0, 1 inside the total space, 0 will goes to x0, and 1 will go to something which by phi will goes to f of x0. So we are in the same fiber. Okay, so this is classical things about coverings and like some things like this. And what I want also about this vibration is this condition, which is crucial, but I will not be able to prove to you here how it is crucial. But I sent to you some notes about this. There is a third condition. Not only the path can be lifted, but we can lift homotopies. And this I will not enter in details here just now, because nobody will be able to follow me, and will not have enough time to go to the important part of the lecture, of the talk. So there is what we call good vibration. So I can skip this. And what are the usual good vibration? You see, if I take a closed subgroup inside a topological group G like this, and I take the canonical morphism surjection from J to J over H, we have here a vibration, which is good. And the same if I take a morphism, surjective morphism from a topological group to another, such that the kernel is discrete, then here also is a vibration, good vibration. And here again, if I take two closed subgroups which are in this way, I have here also a good vibration. The maps are easy to G. I send, if I take the class of G modulo H1, I will send it to the class of J modulo H2, and this is well defined since H1 is computed in H2. And all the fibers are modeled with respect to H2 over H1. So here we have a nice vibration. And why we are looking with nice vibration? Because we have a very important thing with vibration. We have the fundamental long exact homotopy sequence. So in a very quick way, let me erase this because I will not be able to go inside. If you have a vibration, which is good, and if we take zero, yes?
A question. What are the discrete kernels? How you define it?
What?
What are the discrete kernels? In the last slide, you mentioned discrete kernels.
The kernel of, I have the kernel of a surjective morphism between two groups, G1 and G2, which are supposed to be closed groups inside GLNK.
And these are discrete. What do you mean by discrete?
Discrete, that means topologically, if each point is is alone. That means it can be put inside an open set which separated from the rest. For instance, Z is discrete in R. Okay. A discrete subgroup or a discrete set is each point is closed and open at the same time. Okay, with respect to the induced topology, the trace topology, the relative topology. Okay, so a discrete subgroup is always closed, and if we have a discrete subgroup as a kernel, we have here a nice vibration. Why these vibrations are called nice? Because we can write for a vibration a long exact of homotopy sequence. Okay, so let me tell you again. I take the fiber here. So let me see. I'm sorry. Here you have the fiber. Here you have the total space, and here you have the basic space, and you have the vibration phi. So you take an element x0 here. Okay. And you take the fiber which passes by through it inside of T, and you have the injection of the fiber inside of T, and you can get all these sets are quite good. B is pointed with respect to phi of x0. The fiber is pointed with respect to x0. T is pointed with respect to x0. And if you look at this sequence of groups or pointed sets, it is an exact long exact sequence. Let me go again. I haven't defined yet what is P2, but accept it with me that it is something which is called the second fundamental group. Okay, and you have here, since F goes inside of T inside of F, you have the usual functor which given by the P1. So we have nature. These maps are clear. They are more homomorphism of groups. I have already said that the P1 is a covariant functor from the category of pointed sets to the category of groups. So these are quite good. Which is not very easy. It is what we call the connecting morphism here, and we will accept that they exist and make this long exact sequence exact, long sequence exact. And let me tell you, F goes to T goes to B, so P1 goes to P1 goes to P1. It's the same for P0, P0. Here we have something which would be P2 of T equals to 0, and before it is P2 of the fiber, etc., etc. So it's a long exact sequence, and I have just made, if you want to remember this, keep this in mind. A mnemonic tool to remember this exact long sequence is it's like a river. Okay, it goes from up to down, 2 bigger than 1 bigger than 0. A river goes from high and goes to, so the water is going like this. Okay, from high to small. This is the first. So it is a quite long river, and what you should understand in the situation that the nice thing is that what we will look at is essentially what happens at the mouth of the river, and this is where the land is the most fertile. Okay, so this is what we will have to apply in our situation. Let us pass now to the second part of my. I need still an example, and here I will tell you what is classical groups, classical Lie groups. There is a result of Van Neumann, which is the following. If you take a closed subgroup in GLNR, then it is a submanifold. That means it's very regular. It has a shape nice. It hasn't singular points like a cone like this. It cannot be like this. It is very nice. Every point has a tangent space. We are in the situation of a submanifold. And therefore, our group will be a Lie group. A Lie group is a combination of a manifold and group structure which are compatible. In the case the group is a submanifold, everything will be fine. We'll have a Lie group. And we'll call these subgroups by the following. If it is closed, it will be a submanifold. And these subgroups are closed subgroups of GLNR. I will call them classical Lie groups. They are Lie groups, and they are classical since they appear as a matrices group. Okay, and what happens that when you have a Lie group, there is a point which is privileged, which is the neutral element. If you have here the tangent space at E, and it is denoted usually by J, it is a Lie algebra, and you have an exponential which goes from G to J. And here, in the case of a closed subgroup of GLNR, we have exactly what is the Lie algebra. It is this. It is the set of all matrices in GLNC such that exponential of Tm belongs to G whatever T, for all T. So now I give you two examples. If I look at SLNK, it's the set of all matrices of determinant 1. It is not difficult at all. It's a good exercise in elementary differential geometry to prove that this set is a submanifold of dimension n square minus 1. We have just one condition, so we lose one dimension, and that its tangent space at the identity is a set of matrices of trace 0, okay, which is denoted by Gothic letters. SL, capital letters, small SL is the Lie algebra. The same happens with the group ON or the group SON. This is the connected component of the one inside of the identity of GLN. These two groups are closed. They are Lie groups, and we can prove directly that they are submanifolds and they have the same tangent space, which is the set of all matrices which are antisymmetric. Okay, so here again, we don't need to apply the von Neumann theorem to prove this. More difficult because we have conjugation here. If we take the unitary group UN, it is also a closed subgroup inside of GLNC. It is even compact, and the Lie algebra is the set of all anti-Hermitian matrices. Anti-Hermitian matrices it's a real vector space of the dimension n square, exactly the same dimension of the Hermitian spaces. So you have UN is classical Lie groups of dimension n2, and its tangent space, its Lie algebra, is the set of anti-Hermitian matrices. If you take SUN, so you must add to this condition the fact that the trace of M equals 0. So all this is quite classical in some sense. Let us go now to the universal covering of SO3. SO3 is a group of rotation. This is a very famous group. You use it everywhere in robotics, in elementary mathematics. It's the set of all rotation in the space, okay? Linear rotation. And here we have a very interesting short exact sequence, which take the unitary, special unitary group to SO3, okay? And it has a kernel which is reduced to plus minus identity. So this map must be well studied. And what we have is SU2. Let me tell you that SU2, if you could look at it as a group of matrices, it will look like the following. What we are seeing is the set of matrices Z1, Z2, minus Z2 bar, Z1 bar conjugate, okay? And this condition, which makes us see easy that topologically is the same as S3, which is the unitary sphere inside of C2. Z1 and Z2, these conditions characterize this inside of C2. So SU2 topologically is nice. It's the third dimension S3. And it has what we call a covering upon SO3. And so we can see, using the long exact sequence, if we write it, we have P1 of plus 1 goes to P1 of SU2, goes to P1 to SO3, goes to P0 of plus minus E2. This is 0 because it's discrete. There is the connected component is exactly what is happening around 0, and around the identity. So this is 0. So sorry, P1 of this is the kernel. So we see from this that the P1 of SO3 is exactly C2, the Z over 2C. Okay, so I'm sorry, I have written. If we take it again, the long exact sequence, just at the end of it, we can prove very easy that the fundamental group of P1 is equal to SO3. This should be could be illustrated by what we call the assiette à soupe. I don't know how you say it in English. That means if you take assiette à soupe.
Bowl of
What is
bowl
a
of
bowl,
soup.
a soup bowl? If you put it here inside your hand and you turn it twice, you see, if you turn it twice, you come back to the first position. Your arm doesn't turn twice. So this is a way to illustrate the fact that P1 of SO3 is equal to Z over 2, 1 plus 1 equals 0. You go back to the same position. So
Sorry, I hate to interrupt, but you have like 5 minutes.
5
to
minutes?
Finish.
Okay, let me, I still need a little bit more of than 5 minutes. Give me 10 minutes, Hania, okay? So what is nice also to see is the following. SO3 is homomorphic to the projective space of dimension 3. Why? Because if you take, usually, let me show you something. If the P2 of R is usually made by all the lines inside of R3. So you can take just half of the sphere and make this appears as the same. Or half the sphere is exactly a disk in which you can get these things identified. So if you want to have P3, it's the same. You must work the same. You take this. You take a ball, okay, a ball of the dimension 3 of R. And that way, we will prove that it is the same as SO3. Why? Because any rotation in the space is given by an axe which you have oriented it and an angle which is in 0 pi. Okay. 0 pi, that is exactly the same because 0 minus pi and plus pi, if you turn, you have what we call a reflection with respect to an axe. So this is another way to see that the P1 of SO3 is equal to Z over 2Z. So this is important. So now let us see SON. SON over SO n minus 1 is S2 Sn minus 1. We write the long exact sequence of homotopy. We find that by induction that SON has the same, because this one is simply connected. We get this, and you arrive till SO3, and so we see that all these groups have Z over 2Z as their fundamental group. If we work with UN, we have the same here. Here is simply connected. You write the long exact sequence and you put that SUN is simply connected. UN is homomorphic to S1 times SUN. So UN has as a P1, the product of the P1 here is simply connected and the P1 here is Z. So all this is classical. Just a last example. Have I time or I stop here? 5 minutes? 3 minutes? Okay. If we take the space of complex symmetric invertible matrices, this is a surprising space. Why are we looking at it? it is not difficult to see that if I have a symmetric, complex symmetric matrix, it is congruent to the identity. That means S can be written as this by letting I take all the symmetric matrices which are invertible, and I let act Gn by PS equal PST of P. We know that any non-degenerate quadratic form on C is equivalent to the standard one, and from this we can get this equality. SNC is homeomorphic of GLNC over ONC. I apply, of course, the theorem on group action. We have all the conditions to have this homeomorphism. So I want to check what is the P1. I write again the long exact sequence, and I prove that it's P1 is equal to Z. That's all. I'm sorry, I haven't been able to go inside the details, but you have what is necessary with my Beamer and with the notes I sent. Any question?
Right,
You see, the subject is really quite good. What you need, first of all, to penetrate it in a good conditions, linear algebra and bilinear algebra. So you have to understand exactly what are the facts about basic reduction of unitary matrices on orthogonal matrices. Essentially, you must understand quite well what happens for what we call normal operators. That means operators which commute with their adjoint. You have a reduction about these operators in a Hermitian vector space or in a Euclidean vector space. And once you have understand the linear part, you need a topological part, which is about quotient spaces, topological connectedness, compactness, etc. You mix the both, and you have a very still something very important to work with. It is what we call the differential geometry at its elementary aspect. That means submanifolds. When you mix all this, you have what we call the linear Lie groups. But still, you cannot stay inside this area, because at the moment you need to work with manifolds and not only with submanifolds, because when you have a Lie group, which is a classical Lie group, and you quotient it by a closed subgroups, the quotient J over H doesn't appear as a submanifold. You need to prove that you must work it as a manifold. And this is very fantastic, why you need to pass from submanifolds to manifolds. And working with the manifold, with the Lie groups, it's very important for physics and for mathematics.
Okay.
This is
yeah. Go ahead.
Okay, so can you give a very simple example of non-classical group with
yes, there is. It is not a very easy example, but if you take SL2R, okay, SL2R. Let me just 1 second. SL2R. This is a linear group, okay? Everything is fine. It's the set of matrices of determinant 1 inside of matrices 2 by 2 matrices. And you take what we call its universal cover. That means the simply connected group, which is over SL2R. And if we look at SL2R, what is its P1? SL2R is isomorphic to SO2 times R to the power D, okay? So SO2, its P1 is Z. So the kernel here will be Z. So you have here a short exact sequence which connect the universal cover of SL2R and SL2R. And this group cannot be realized as a matrix subgroup. There is no realization of it as a linear group. It cannot be put inside a linear group. A group of GLNR. You cannot realize it as a classical linear group. The universal cover of SL2R is not a linear group. Did you have the answer?
Still we can, yeah, so this is very interesting that still we can construct non-linear groups and non-classical groups starting from these linear groups.
Yes, you begin with SL2R, which is not so easy, but it's a fundamental group. There is a book of Serge Lang, which is devoted completely to SL2R and its representation. And if you take the universal cover of SL2R, you get a group which is not linear.
Thank you very much.
But really, I insist, I'm not a very good able to speak in English, as you see, but this material is really, really nice to work with. There are many books about this matter now, which are available for students. And I tell you something very important. You cannot go inside seriously if you don't have a good basis in linear algebra, in topology, and in differential geometry. And this is why this part of mathematics is really nice, because it is good for good students who have been able, through their undergraduate studies, to absorb the good material about all these matters.
Right, thank you. Are there any other questions?
Please take time and read the beamer and
Can you say some more about reductions on the linear algebra side?
About
reductions or linear maps on the linear algebra side?
I haven't been able, I don't.
Can you say more about reductions?
Linear algebra reduction. Okay. First of all, what you need here in this context is to know that if you have a Hermitian vector space, a vector space which is n-dimensional C vector space. Okay, it is a vector space over C, and it is equipped with a Hermitian form. So here you are working with GLNC essentially, and you have the application, what we call the adjoint of the matrix. The fundamental basic fact is the following. If you take these matrices, M, if it is like this, we call it a normal matrix. That means it commutes with its adjoint. M star is Tm bar, okay? And these matrices are always can be reduced to a diagonal form. Okay, these are exactly the matrices which can be reduced to diagonal form with a unitary matrix as that means there is an orthonormal basis with respect to the Hermitian product in which the matrix is diagonal. Once you have these, there are a lot of examples of these matrices. Let us say if M is Hermitian, it will work. Anti-Hermitian, it will work. Unitary, it will work. Okay. These matrices have what are the Hermitian matrices? They are the normal matrices with real eigenvalues. What are the unitary normal matrices? The matrices which are normal and with the eigenvalues in the unit circle. So this is fundamental to understand how it works, and you must work with the real version of it. what are the matrices like this, which commute with their transpose. Here you cannot always diagonalize, but we can put it as a diagonal part with what we call similarities. That means matrices of the form lambda A B minus B A. Like this row cos theta, sin theta, minus sin theta, cos theta. So these are the matrices you can get. So once you have, here in France, people work a lot during their first year university about these matters. There are plenty now of books who treat these material. I think that it would be very helpful for your students to have a good reference to it in English, just by translating something already existent or looking at the enormous mathematical English library where these things are done. But in France, really, they are very well studied, and there are many good expository arguments and sometimes very nice proof for some results which are quick, and one may discover them and be happy about them. I have written in the 80s a book with one of my colleagues, late Frédéric Testard, and it is still a good reference for the subject. It's called Introduction to Classical Lie Groups. And if you read French, it is an excellent reference. If not, I am sure that there are plenty of references which tackle these matters. And this is the part which is needed to understand what happens in this context, what we call the bilinear algebra associated with a Hermitian space. The topology, we have seen the topology. We have connectedness, quotients, the theorem of the equivariant map, which is very important, Baire theorem. All these are really interesting and constitute the core of the matter. As for the differential geometry part, it's not difficult. If you work with your students with SLNR and SON and prove that they are submanifolds, it's already a very nice example, and it's easy to establish. And you compute the tangent space of the identity. You discover that it is a Lie subalgebra for the bracket AB minus B1, AB minus BA. And so you have a lot of examples which are worked concretely. And so you have a very good intuition about what is happening. And in all this, the exponential map is fundamental. The exponential map of matrices is a fundamental tool.
Okay, I have a layman question in this particular area, in the sense that when we have algebraic geometry tool, and with the understanding of pi 1, pi 2, what we compute in algebraic geometry, now the things are being connected when we are computing pi 1, pi 2 through of these matrices group SU, SON. So how one come to this particular conclusion of F pi 1 SN cross is how Van Kempen theorem help us to compute the fundamental group of these matrices groups. Do you understand my?
When you use this long homotopy exact sequence, appears at one place or another a sphere. So to understand what is happening with respect to these classical Lie groups, you need, of course, to have already studied what we call the homotopy type of spheres. Everyone understands that the P1 of the circle is equal to Z, and for the sphere, it is simply connected. Its P1 is 0. But if you go to upper places, you can still use the homotopy, the long exact sequence combined with classical groups to compute what has happened for big spheres S3, S4. But once again, if you need to compute P2 of S3, P2 of S3 is equal to 0 also. This is intuitively acceptable. You see, you have a sphere of dimension 3, and you take the homotopy classes of not loops, but what we call a 2-degree loop. That means a loop which is defined on the ball and which is constant on the boundary. So these things, if you have already studied have a good course on algebraic topology, you can go ahead. But you see, the fundamental groups of spheres are not completely known. It's still open for many parts of it. But at least P1 and P2 for spheres is already done. And you see, you arrive always to what I call the mouth of the river. That means at slow dimension, as the extreme part of the long exact sequence. You don't need to go far away from it. At the level of P2, P1, and P0, you can completely, by induction, reduce lots of things.
And just a note about the fibration. So all these groups have a fibration, a library of fibration of these matrices.
You see, a fibration usually is called what you call a good fiber bundle. You see, which is trivialized locally, etc. I haven't entered like this because I don't need. All I need is that I have a good fibration, and why all fibration which are met in algebraic topology at good fibration.
And do they have any relationship with the covering spaces like we have in algebraic topology?
About covering?
Yeah.
Yes.
And
if you have a discrete,
discrete one has
this is what we call covering. Okay. And usually we call it fibration. But when we have what we call a fiber bundle with a group, structural group, which is a group which is acting on the right freely, we have the fibration I have shown to you. H2 over H1 goes to G over H1 goes H2 goes to G over H1. These fibrations are what we call principal fiber bundles with structural group G acting on the right freely. You can see this in Kobayashi-Nomizu. So what practically here, what is nice is that you don't need to enter in all the details of algebraic topology. You have fibrations by looking at by nested closed subgroups H1 inside of H2 inside of G. They are what we call closed subgroups. You have fibrations which are canonically associated to them. The fiber is H2 over H1. The total space is G1 over H2, and the base is G1 over H1. And in that case, you can apply your long exact sequence of homotopy and get a lot of results.
And what about the role of the underlying topology? So all in your discussion, you were using the usual topology. And initially, you were discussing about the Zariski topology.
Yes. What's happening? You see, if you have what is the usual topology? The usual topology is the one we live with. That means the topology on Rn.
Yeah.
It is induced by the metric structure of Rn associated to any norm.
Yeah,
and this is what we call the usual Hausdorff topology compatible with the structure of vector space of dimension finite. Now, if you are working with algebraic geometry, you have you focus your interest on polynomials. And you don't, let me tell you, if you look at the zero of a polynomial, this is in one variable, it's a union of finite points. You see, this is clearly for the usual topology finite, closed. If you are working with two variables, let us say you look at the set of points Z1, comma Z2 in C2, and these you get what we call the usual Zariski topology, which has as basic sets the complementary of the complement of the zero of polynomials. These are the basic. You have a topology, and for this topology, an open set is open for the usual topology. So if you have, for instance, a function which is zero on a set, on an open set in Rn, it's not zero.
Mhm.
You can have what we call something which is zero
Yeah.
at the, and not zero outside. But for polynomials, if it is zero on an open set with
Mhm.
2 or 3 variables, it will be zero everywhere else.
Mhm.
Why? Remember the fact that a polynomial has a Taylor expression which stops, and if all if the polynomial is zero in the neighborhood, all its derivative at the point inside this open set will be zero.
Mhm.
So these make the Zariski topology more rigid than the topology of the usual topology. The fact as once you have left R and C and QP, the p-adics aside, you want still to have some reasoning which can work in other groups, in other cases, fields, even if characteristic zero, finite characteristic. So in that case, you cannot appeal for the usual topology. You need to have a new topology, and this new topology is adaptable to the algebraic case. It is called the Zariski topology. And it is good sometimes to mix the two together when you are working with R and C.
And a few words about its application in the sense of representation theory.
This has, you see, this field is completely huge, okay? I have looked at some aspect of homotopy properties, but if you want to see what happens when you are working with what we call representation theory, here will appear what we call continuous representation theory, because the algebraic part will you cannot work while you are working with Lie groups unless you go to the Lie algebras, which are what we call the linear approximation of them. And in that case, if you want to go back from the Lie algebra to the group, you need to integrate. This is possible if your group is simply connected, but it's no more possible if it is not, and appear finite groups and representation of finite groups. And when you are working with continuous groups like SL2R, for instance, the representation theory, you will work with Hilbert spaces, and you will work with operators which are defined on a Hilbert spaces, and you will see if you can have representation theory, and you have what we call in classification of irreducible representation, the principal series, the complementary series, etc., etc. And this is done quite good in the book of Serge Lang about SL2R. And this is analysis, okay? You are here expressly inside analysis. And you can still work on operator, differential operator theory. It's a huge part of mathematics, but nowadays it's not really, people feel that they have already done all the most important theorems, Plancherel theorem, differential operators associated with the heat equations, with the with a lot of Schrodinger equations, etc., etc. You can work them on Lie groups, but now people are much interested by categorical approach, all this with triangulated categories, and you must invite Bernhard Keller to tell you about this, but he has left the room because he has.
We already spotted him.
He left me alone, and he went to another seminar online, which appears every Monday afternoon. I'm sorry, but really, this what I insist for young students: go inside this part of mathematics, learn the basics quite well, and you will be happy to discover all the richness and the beautiful results which appear in this context.
Thank you, Professor Rashid. Thank you very much. As usual, this is a wonderful seminar. Just
you are very nice, Imran, to tell me this, but it was an opportunity for me to recall all these old souvenirs. I was working with this when I was 20 years old, and now I was very happy to read them again in order to prepare my talk.
In any case, we were missing to see you live here on.
If it was live, it will be easier. I will.
Yeah, using the board, everyone will enjoy it. And just a small announcement for the participant that Professor Rashid has shared the lecture notes for this talk as well as its previous talks. If someone needs those lecture notes, they can write to us on mathevents@lams.edu.pk. So in response to that email, we will send you the notes, as well as those who need the recording of his lectures, previous talk and this talk. So those videos are also available. Professor Rashid, if you need it, you will get it too.
I don't want to look at myself. This is, I will be depressed. But what I can tell you, I will send to Mrs. Hania the beamer, the PDF beamer without all these things, because the beamers are a little different from the PDF of the notes. I think if you combine the PDF of the notes with the PDF of the beamer, you will have a good introduction to the subject. And you can look, if you want to smile and laugh at me at the registration of my talks.
No, thank you very much. Thank you very much. Yes.
I wish to. So I wish you happy birthday today. I think it's also your birthday. So
thank you.
It's a good.
It's Imran's birthday.
Yeah, it's a perfect birthday gift for me.
Okay, happy birthday, Imran.
Thank you, thank you, thank you, thank you.
Thank you.
Now, over to you, Hania. Now,
Hania, where is my friend Yahya?
Well, he's gone outside to play with his friends. Okay, we need to formally say bye to you and thank you for this insightful, wonderful lecture. So yeah, thank you all for joining us.